Given a lowercase string s. In one move you may swap any two adjacent characters. Output the minimum number of moves needed to turn s into a palindrome. Example, s is A, B, B. Swap the middle adjacent pair to get A, B, one move. Swap the next adjacent pair on the right to get A, B, A, which reads the same forward and backward. That is 2 moves in total. Trying to map every single possible swap combination to find a palindrome triggers a brutal combinatorial explosion. For even a moderately sized string, the search space grows factorially. We need a definitive property that avoids searching entirely. The key is shifting our focus to the structural constraints of a palindrome. A palindrome is defined from the outside in. If we can successfully pair the outermost characters first, we can lock them into place and solve the smaller remaining subproblem inside. So, what's the optimal choice? Let's be greedy. We lock onto our leftmost character, and we scan from the far right edge backward to find its very first identical twin. Once found, we calculate the number of adjacent swaps needed to shift that twin all the way to our right boundary. The exact cost to bubble this character into its final right-hand slot is simply the distance between our target boundary and our character's current position. By executing adjacent swaps, we satisfy our outer boundary match in exactly 2 moves, leaving us with a clean inner string. But what happens if a character has no matching partner? In any valid palindrome string of odd length, exactly one unique character must stand alone. If our backward scan can't find a duplicate partner, this character is destined for the absolute center of our finalized palindrome string. By repeatedly matching the edges and contracting our boundaries inward, we guarantee a globally optimal minimum move count. We set up our workspace with 2 tracking boundaries. Our left pointer initializes at the very first index, and our right pointer anchors to the final index. We also establish a running counter to track our total swap operations. With our left pointer locked onto A, we look for its rightmost duplicate by scanning backward from our right boundary. We find it immediately at index 6. Since it is already at the boundary edge, 0 swaps are required. We lock these matching edges in place and contract both of our pointer boundaries inward. Now our left pointer sits on the letter B at index 1. We scan backward from our right boundary at index 5. The character at 5 is X, which is not a match. We continue to index 4 and find our matching B. When current falls strictly between left and right, we bubble it outward with adjacent swaps. Here the partner at index 4 swaps once with index 5. The letter B slides to the right boundary, and the string updates in place. That single adjacent swap completes the bubble. The cost formula gives right minus current, 5 minus 4 equals 1. We add that to our running total and contract both pointer boundaries inward. Next, left points at the letter A at index 2. Scanning indices 4 and 3 finds no matching A. This character has no twin in our window, so we apply the center rule. Floor of 7 over 2 minus 2 equals 1, and only the left pointer advances. Our window is down to indices 3 and 4. We match the twin X at the right edge with 0 swaps. Our pointers meet, and we return our total minimum swap count of 2. Remember the fork. When a twin exists inside the window, bubble it with adjacent swaps, then count the cost and shrink both boundaries. When no twin exists, count the center cost only and advance just the left pointer. Swaps follow partners. Count alone handles the center. N is the length of S, time is O of n squared. Worst case, each outer step may scan backward and bubble a partner across the remaining window. Space is O of n for the working copy of the string we swap in place, plus O of 1 for the 2 pointers and counters. Function min moves to make palindrome takes the string S. Build a mutable copy CS so we can swap characters in place. Initialize total swaps to 0 and set left and right to the window edges. Repeat while left is still strictly less than right. Start the backward scan from the right boundary. Move current left until it matches the character at left. Decrement current by 1 on each mismatch. If a real twin was found, not a center collision. Bubble that partner outward with adjacent swaps. Exchange the pair at current and current plus 1. Add 1 to the swap counter for each exchange. Advance current 1 step right after each swap. Contract both pointer boundaries inward. Otherwise no twin exists inside the window. Add the center shift cost without swapping the string. Advance only the left pointer past this character. Return total swaps as the answer.